Started, it's the time, and welcome to the second ISC GSDS seminar. And my name is Kwon Chang-hyun, and I'm the organizer of this seminar series. And this time, this talk is jointly sponsored by the Discrete Maths Group from IBS. And let me introduce today's speaker. I mean, he doesn't really require any introduction, but just in case any of you are not familiar with this speaker, I will tell you a little bit about him. He made numerous contributions to the combinatorial optimization world, especially on the TSP related topics. And he is the main developer of the Concord server. I'm sure that you have used some moment Concord server for your research. And he has written three outstanding books in the topic, and then I have all three of them. So that tells something about him, I think. And he's a fellow of the outstanding academic communities, a fellow of INFONS, fellow of SIM, and fellow of AMS. And he's also a member of he's a part of the National Academy of Engineering from the United States. That's quite a highest honor as an engineer can receive. So, with that, let me please welcome Professor Bldg.
Thank you, and thank you all for coming. It's really great to be here at KAIST. My first trip to Korea. It's been very nice. So, the traveling salesman problem, or I'll call it TSP for short, it's simple. What's the shortest route to visit some of Daejeon's top sites and come back to your starting point? So, the shortest possible circular tour. I mean, that's crazy simple, right? You can go take map software, and that'll give you the shortest path between 2 points. So you just need to put those paths together into a circular tour. So there were 10 stops, 10 locations. So you can start anywhere you want, and you have 9 choices for the first stop, 8 choices for the second stop, and so forth. You multiply those together, there's only 360,000 possible routes. That's not very much for a computer to check. So very easily compute the shortest possible tour. It's a simple problem. Yeah, but the TSP is actually one of the most studied and famous problems in applied mathematics. Part of the reason is that they're just natural applications. You know, in your daily life, you look at TSP, right? You're ordering what chores you're going to do that day. The first mathematics paper ever written on a TSP focused on an application. It was in farming in India, sampling the soil. If you go out on the street, you can see the TSP in action. You have delivery vans bringing things to your home. In the United States, the Amazon drivers cover about 150 stops a day in a TSP tour. And finding short and safe routes for Amazon was important enough that several years ago they ran a competition, a worldwide competition with a $100,000 prize that attracted over 2,000 participants, all trying to find better routes for Amazon's drivers. And it's not just moving people or equipment around. The problem arises in genome sequencing, or in machine scheduling, or in data analysis. Pretty much any time you have to put things in order, there might be a traveling salesman problem. What I'm showing are some of the companies that have obtained license to our Concord solver, written together with Bldg, Bixby, and Quatel. We give the code away for free to firms as long as they're willing to tell me how they're going to use the code. That way I get a new application every week or so. So the strict applications are very nice, but that's not the full reason why the TSP is so famous. It also serves as a central problem for discussing complexity. So for discussing possible limits to computing power. For example, several years ago, in 2019, the World Economic Forum in Davos put out a report on the future of supercomputing. The one-line summary mentions the TSP. Last year, NVIDIA, so NVIDIA makes the GPU cards that drive all of these AI things you see in the newspaper. They ran a developers conference for AI, some 250,000 participants. The boss of the company, the CEO, gave a talk, and first he had these cool graphics, IMAI, and then he started talking about the TSP to show off how powerful their hardware is. In the popular newspapers, the popular press, traveling salesman problem means impossible to solve. So the Washington Post says to solve a 22-point problem takes 1,000 years. In this context, that 10-point problem I said was misleading. It's a 10 points you could check every tour. But suppose instead of visiting the Daejeon, you want to, like myself, you want to see all the high mountains in Korea. Well, there's 384 of them. So with 384, there's 383 factorial possible peaks of 5,000 meters. So even if you had all the computers in the world, you can't possibly look at all of them. So it's impossible to solve the problem by looking at each tour one at a time. But that doesn't mean it's impossible to solve the TSP in this case. But think of sorting numbers. Right, to sort n numbers, you don't need to look at all n factorial orderings to figure out the right one. We have different ways to sort. Same with the TSP. There's different ways to attack the problem. And for this particular example, from 384, I actually computed the shortest route. It takes about 65 days to walk around Korea to see all those mountains. We have a friend over here that's going to do this for me. Yeah, but and the compute that took less than a second on my Mac Studio. Going way larger, Professor Tang-O found for me all the pubs and bars in Daejeon. And the route for that only takes 58 hours and took a little over a minute to solve. So obviously I'm not checking all the tours one by one. The technique I'm using goes back to Danzig, Faulkner, and Johnson in 1954. Next month will mark the 7th anniversary of their paper. And I'm always really struck when I look at their paper, because I just can't believe they did this. They solved a 49-city traveling salesman problem by hand. There were no computers then. They not only solved it, they made a one-page proof that is optimal, as short as possible. Right? And this is a big result in discrete optimization. And at the time, it appeared in various popular journals. It was a very celebrated result. One of the main things I want to do in the talk is describe their technique and what we're doing to push it out, solve even larger, more difficult instances. But before I do that, I want to talk a little bit about the history of the TSP. How did this become the icon of complexity? It started at a very interesting place for mathematics in Austria. Mathematics was part of a larger group of philosophers and scientists called the Vienna Circle. The lead mathematician was Karl Menger. If you work in graphing, you might know Menger's theorem. It's that person. Karl Menger was the great mentor of, his star student was named Kurt Gödel. Gödel is famous for making the incompleteness theorem in logic. 1930 was the year Gödel announced that theorem. That same year, Karl Menger posed the traveling salesman problem. And he talks about the geometric version. So you have points in space, the distance, the travel distance is the straight line Euclidean distance. And what he asks is the most natural question. Can you solve the problem without looking at all the solutions one by one? And this is actually a deep question. At the time, mathematics was interested in existential questions. But certainly an algorithm exists. You can just list them all. Right? He is asking for a better than finite algorithm. I mean, keep in mind this is before complexity, before Alan Turing. Right? This is really, in my viewpoint, one of the starting points of complexity theory. So, if n factorial is too slow, what function of n would be good? Well, here the gold standard was laid down by John von Neumann. He solved a relaxation of the TSP that ran not in n factorial, but in n cubed time. N cubed is much faster than factorial. So strengthened form of Menger's question is, can you solve the TSP in n to some fixed powers, n squared, n cubed? So polynomial time algorithm for the TSP. Well, already in the 1950s, Merle Flood, a big pioneer in operations research, thought that that's probably impossible. In the early 1960s, IBM put out a press release saying this is long-defied solution. 1967, Jack Edmonds flat out conjectures you'll never be able to solve the traveling salesman problem. So no polynomial time algorithm. A few years later, Richard Karp proves, using complexity theories now developed, proves that the traveling salesman problem is NP complete. So now Edmonds' conjecture is wrapped up in this big P versus NP problem. Right? It's a little bit delicate to explain exactly what this is, but this is one of the greatest open problems in mathematics. And if you find a fast algorithm for the TSP, you'll win a $1 million prize. Or if you prove the algorithm doesn't exist, $1 million prize. Even Hollywood was interested in actually a proof that P is equal to NP. Oh, I was hoping the sound would be louder. It's not coming through the speakers, it's just coming through my computer. Okay. But anyway, it's just that you don't need to know the sound too much. It's just it was a thriller movie, Hollywood movie, set around the consequences of a fast TSP algorithm. Fast TSP algorithm, you could break cryptography, get into banks. So the question is, where do we stand now? So these are all challenges. How quickly can we solve the TSP? Well, maybe it's not known to newspapers, but in fact, Menger's first question was answered in 1962. You can do better than n factorial. So Richard Bellman and independently Helen Carr both found algorithms that run an n squared 2 to the n time. It's exponential, but that's much faster than n factorial. Right? And their algorithm was simple, used dynamic programming. It builds, I could spend 5 minutes and convince you of it, but it builds the solution from small bits, puts it together into a full Tor. The remarkable thing is, there's been no progress. That's 62 years ago. Very simple one-page algorithm hasn't improved anything. No improvement in TSP complexity. They're still the champion. So then you could ask, well, okay, maybe I don't want to solve the problem. I just want to come close. Can you find a Tor in polynomial time that's guaranteed to be close to optimal? Well, the answer in general is no. But in a very natural case, you can at least get within 50% of optimal. So 1.5 approximation. The special case is called a triangle inequality. It means go from A to B shouldn't be any longer than first going to C then to B. Which makes sense, because the distance A to B should be the shortest path. It's called a triangle inequality. With that, you can find a Tor by first connecting the points in a tree, then using matching to pair up odd nodes in the tree. You get a Eulerian graph that then find a Tor, and that gives you a 1.5 approximation. This is due to Nicholas Christofides. Like Bellman held Carr, this stood the test of time. There's no improvement in 44 years. Yeah, and it's not that I'm bad at addition and subtraction, because there was an improvement 4 years ago. A group of computer scientists did use very sophisticated methods. Yeah, this was very difficult. It's like a 70-page group, very sophisticated, just epsilon, just a little better than 1.5. Right? So this is actually a big breakthrough. It's not clear whether 1.5 could be broken. It can. But I think I want to emphasize that this is theoretical, not meant to use. Being 50% of an optimal Tor is not a good Tor. Right? You don't want to do that. So suppose you want to visit Korea. I just want to find me a short Tor. I don't care about a math guarantee. Just give me a short Tor for this example. But that's actually a very widely studied topic. Right? There's many, many papers written each year. Even in biology, there's papers showing how bees and slime mold and various things can solve the traveling salesman problem. But what they mean is 4 or 5 points. Sometimes they have good quality, but you should not in any way think that you should get slime mold to solve your traveling salesman problem. It's not a good idea. If you want to solve the traveling salesman problem, you want to turn to modern heuristic methods. Sticking with the animal kingdom, Curious George actually knows the main idea.
Four leaves, clean a garage, wash windows, stack some cans. What's the matter?
See, what George doesn't like is that the Tor crosses itself. And in the traveling salesman Tor, the crosses, you should delete the crossing edges and reconnect the path. With the Pythagorean theorem, you get a shorter Tor. Right? And Merle Flood, the same one I mentioned before, turned that into an algorithm called 2-op. Forget about the geometry, just try deleting 2 edges and reconnecting. You get a shorter Tor, you go to it. So it's a local search algorithm. You're searching around the neighbors are the ones you get by 2-op, and you get better you go. So it's like hill climbing. So if I want to find the highest place in Daejeon, I don't first jump down here, like we're going down. No, I would go up here, right? This would be higher. And if I was really trying to get higher and I was younger, I might jump onto that. So it keeps getting higher. But you see, the trouble with local search is it doesn't necessarily find an optimal solution unless I can look further. If I look further, I go all the way to the back of the room, it's higher. And that's what do in general. So this is how it works on 2-op. It keeps repeatedly doing those swaps, and getting a better tour. That's like looking at the small neighborhoods. Looking at a bigger neighborhood, Lynn and Kernighan do a version of a K-op, where there's leading K edges. You see how this very quickly will clean up this tour. So it takes bad tours and turns into good tours. So it's this local search hill climbing, a long history of improvements. The champion here is by Kel Helskin. It's this code LKH2 that gives you very good tours quickly. No guarantee that they're optimal, but works well in practice. His algorithm and local search in general was the starting point for our submission to the Amazon challenge. Now I should explain that Amazon wasn't trying to get the shortest tours. If they were trying to get the shortest tours, I would just use Concord. We could easily solve exactly 150-point problems. They wanted to do something, I was just speaking with Professor Kim about machine scheduling, that sometimes she tells people how to schedule and the workers don't do that, they like doing something different. This is similar for Amazon. That Amazon's drivers, they give them a tour and then, there's some nice cat that they like to pet on their way to work, so they go in a different street and pet the work. There are different reasons why they might not follow the tour. So the contest was set up in machine learning style. They gave us 6,000 routes that the drivers took. And you should use that to learn what drivers like. And they gave us 3,000 routes that you had to then find tours. Then the score was how closely they matched what the drivers did. So this computation was done on an Amazon server. You didn't see the actual existence. So that was a challenge. So you need to look at what the driver's tours do and see, well, is there something unusual? Well, here, I don't know if you can read the numbers. This stop is 145 in a tour. This is 144. The driver went all the way over here to 145 and then back to 146. So very strange. Obviously, the optimal tour doesn't do that, right? This is 98 and 99 and 100. It does it that way. The reason has to do with the colors. I colored the nodes according to the zone ID that's given to the packages. So in the truck, all the packages with the same zone ID get put into one of these bins. And these bins, once they're empty, they can be folded up and put away. So the driver's like to completely empty the bin. So we wanted to do all those red nodes consecutively. So as a first step, we just added a constraint that all the zones should appear consecutively. It adds about 500 seconds to the tour, but you see it's consecutive now. It goes from 99, 100 over to 101 and over to 102. But it gives a better score. So in a competition, a perfect match is 0, and the lower the score, the better. So we formed a team with Stefan Hell from Germany and Kel Helskin from Denmark. And our idea was, well, we now have these zones, now we just have to figure out certain rules that how drivers might like to move from zone to zone. So we built clusters of zones and clusters of clusters, so multi-level clustering, and then precedence constraints between them, all by just looking at the data, trying to figure out what drivers like to do. All right, then, if you look at the competition, you read it, that they really were expecting that artificial intelligence, machine learning, deep learning would outperform traditional optimization, which is what I do. So I was happy that, in fact, we won the competition. We won the $100,000. And not only that, our score was 40% better than the second place score. So it was not to like. I mean, they gave us $100,000. But it was something I didn't like. Amazon made a blog about the competition and said the traveling salesman problem is the most famous NP-complete problem. Therefore, you can't solve it except for the simplest of examples. That's hard for me because almost all my research career was trying to show the opposite is true. That NP hard means that as n goes off to infinity, there might be some bad examples we'll not be able to solve. It doesn't mean that you have a particular example, I can't solve that. Right? And so the question goes back is, well, are newspapers right? Does it take 1,000 years to solve a 50-point problem? Well, there's another line of work on this, on looking at exact solutions to NP-hard problems. And it really goes back to Hassler-Whitney. So Hassler-Whitney is a big god in the discrete math center here. I mean, he invented matroids. The matroids are a big topic of study. He invented them. For the TSP, what he did was took Menger's sort of abstract asymptotic problem about complexity and brought it home, something you could understand. Whitney proposed a specific example of routing through the United States, so the 48 states problem. That became, the TSP was known as the 48 states problem. And it's his version that was then studied by Julia Robinson. So Julia Robinson was a giant in pure mathematics. She's best known for leading the team that proved Hilbert's 10th problem. Very famous mathematician. But as a postdoctoral fellow at the Rand Corporation in California, she studied the TSP. Actually, it's the first time that TSP ever appeared in a published paper. It was hers. And despite her pure math background, her PhD was in Gödel-style logic. She works on not on asymptotics, but on the mathematics to help solve a 50-point problem. So it's 1949, and it was her work that led to the breakthrough by Danzig's team. And the newspaper, the magazine article about it was spot on. The California experts used linear programming to solve the TSP, and that's the tool. Linear programming was invented by Danzig, so this is now 1954. Danzig invented this around 1945, together with the simplex algorithm. The model is very simple, right? You're optimizing a linear function so that it's got linear inequality constraints. If you look in a textbook, the example they always show is the diet problem, where the variables are the number of servings of things you should have per day. The constraints make sure you have enough calories, enough protein. It's important to point out, though, that linear programming doesn't tell you just drink one glass of milk. It might say drink a half a glass of milk. Calculate out fractions. Julian Robinson is the first person to apply linear programming to the TSP. Her variables tell you whether or not you should use the edge. 0 if you don't use it, 1 if you do use it. Well, she has it out fractions. And her constraints say you pick any node, you sum the edges meeting that node, that should sum to exactly 2. Well, because the TSP comes in and out. Exactly 2. It's called the assignment problem. And it's almost magical how this model works for TSP. So this I'm claiming that's the optimal tour. Now, if you read the Washington Post, you would say, no, you're lying to us. We can't solve a 22-city problem in 1,000 years. How did you solve a 100-city problem? Well, the thing is, linear programming not only told me how to draw the tour, it told me the proof that it's short as possible. And the proof is this pretty colored picture. Well, I mean, I picked the colors, the TSP goes in. So how does that prove it? Well, let me zoom in. So you see each node is surrounded by a blue disk, and the blue disks are disjoint. Now, TSP tour has to cross that disk twice, so twice the radius. The other regions, say like that yellow band, that encircles a subset of nodes. So the TSP tour has to cross it at least twice. It could go in and out more than twice, but at least twice. So twice the sum of the radii of the disk, plus twice the width of those bands, is a lower bound for the TSP. The TSP has to be at least that long. If you get out a ruler and measure the length of the tour and the radius of all those disks, you'll see that the two numbers equal. So this is an optimal tour. But you don't have to actually measure things. Just notice that every region is crossed exactly twice, and each edge is entirely covered by the regions. Those two facts mean that the two are equal. This comes from linear programming. The model is called the subtour LP. It starts with Julia Robinson's cyber LP as a constraint for every subset of nodes, saying that at least 2 edges have to meet that subset, greater than or equal to 2. The linear programming values that you get from this draw the tour. The colored regions are coming from a dual linear programming problem, where the Julia Robinson constraints give you the blue disk, and the subtour constraints give you the bands. All right, so the first thing you might say, well, all right, that's a nice model, but how are you even going to write that down? That's one for every subset. That's what Danzig, Folks, and Johnson handle. They have a method called now the cutting plane method that generates the inequalities on the fly as you need them. So the idea is that you get a solution, say, to having no subtour inequalities, If that solution happens to satisfy all the subterranean inequalities, we're done. If not, you add some violated subterranean inequalities and resolve the model. But you still get a relaxation of the TSP. So you see it run now on a 50-point problem. I'll draw both the regions as they're changing and the solution changing. So Julia Robinson's first model, these variables have value 2 because she doesn't say the variables between 0 and 1. So as it goes along, it takes 8 rounds. The solution is changing, and plus the regions are changing. And again, when it's done, the length of the tour matches the bound. And you see everything's crossed exactly twice. Right, so what's happening here is that 2 linear programming problems are being solved simultaneously. One's called the primal, one's the dual. So the primal problem is drawing the tour, the dual problem is drawing the region. So on the tour, you're minimizing, trying to make it short as possible. For the bound, it's maximizing. The bigger the lower bound, the more information you get, so it's maximizing. And the problems are such that, so you're pushing the tour down, pushing the bound up. They're designed so that you can never go past one another. So you give any solution to the dual, gives me a lower bound. That means I don't actually have to solve the problem, I just have to get a good dual solution. Even better, for the TSP, it has a 0 and 1 bounds, which give me 2 identity matrices for the dual. That means I can take any dual solution, say given by a commercial solver, which may not be quite feasible, and I can adjust it to make it feasible. And I use exact arithmetic, so I can always get a valid lower bound. The coolest thing, though, is that von Neumann proved if you push the primal solution down as far as you go, and the dual solution up as far as you go, the 2 are equal, so yin and yang. And you should thank the computational gods that that's true, because that's what allows us to solve the LP problem. The primal and dual certify each other. So bingo, these are all solutions to 100-node problem. Some of them wildly complex, the dual solution. But von Neumann doesn't lie, the length of the tour is equal to the bound. So at this point you might wonder, well, why don't you go and get the $1 million for solving the TSP? The trouble is going back to the half a glass of milk. In the TSP, you might get half of an edge. So the red edges carry value half. So 1, half, sums to 2, but it's not a tour. So the optimal solution to the LP might be fractions. What Danzig, Polk, and Johnson say to do is the obvious thing. They just add more inequalities, right? More cutting planes. What they're relying on is the theoretical work of Minkowski from the previous century, which says something more complicated, but what it means for the TSP is that there does exist a perfect set of inequalities. There's some LP relaxation whose optimal solution would be a tour. The catch is that we actually don't know what the inequalities are. That's why we can't solve every instance of the TSP. But we have big families that were proved over decades of research by lots of people of inequalities that are satisfied by all tours, so you can add them to the LP. So you can see how this works for the 48 states problem. I'll just draw the primal solution. This was not a geometric problem. This was a driving distance problem, so I can't really make those regions. But if you watch it go, you see that there's sometimes islands that they stamp out with subtour inequalities and get more and more tour lag. In only 9 steps, it solved the problem. There were 7 subtour inequalities, then 2 more complicated ones called Combinatorics inequalities. So this is the cutting plane method. You solve a problem, it doesn't satisfy your inequalities, you solve the LP problem. Doesn't satisfy your inequalities, you add some more and resolve. And this is what allows us to solve mixed integer programming problems and many discrete problems. So you have to like the last statement in Danzig's paper. It says, well, maybe it might be useful. Well, it's really modest. This is the most important paper ever written in discrete optimization. Right, so it's not only for mixed integer programming, for the TSP itself. These are the world record solutions, the largest challenges that have been solved, starting with our 49 city problem. It took some years for people to understand what they did, and also for the computers to be developed. But once it understood, the largest problem started increasing. This is a log scale, so the fact that this is a nice linear fit means we're going exponentially fast in how large the problems are. So In the 1980s, it was led by Martin Groucho, Manfred Padberg, and Rinaldi. They had a lot of ideas that we ended up putting into the Concord code. Since 1992, all the records have been set by Concord, with Applegate Fix being fought out, more recently with Daniel Espinosa, Marcus Cuculier, and Kel Helsken. The largest problem has 109,000 points. That's actually three-dimensional points. They're positions of stars. See them rotating around. The distance is the straight line distance. The largest instance that was solved before Concord had some 2,000 cities. That's how I solved it last night. That was only 8 seconds on my iPhone. The 2,000 city problem. Nonetheless, in 2015, newspapers through countries throughout the world all report that solving 50 cities is impossible. Right? They're reporting another United States tour, a driving tour, see sites in the United States. And the tour was a good tour, but it wasn't the shortest possible tour. But they were trying to explain that the shortest possible is impossible to do. And partly you can see why they might be able to think that all these record problems, except for two small ones, these are not driving or walking distances, these are straight lines. Right? And this one the article was about was driving. So in response, they were talking about a 50-point problem. Daniel Marcos and I solved for 50,000 cities. So we had walking distance from Google. We found US historical sites, and then 49,000 some pubs in the UK. The largest one, these are Google Maps. Google Maps, you ask Google Maps how to walk from one place to another. The largest example, a Dutch firm, computed for us the biking distance between every historical site in the Netherlands. So there's 1.6 billion distances they gave us. That's the input. So n the number of nodes, n the number of edges. You have to keep in mind the scale of these things. Right? Just a low-order polynomial algorithm is going to take hundreds of years. But nonetheless, 6 months later, we had solved the problem with the cutting plane method. And by solve, I meant you can't even make it 1 meter shorter. The distance were in meters. So it was this 20 million meters. This is a cartoon that appeared in the major Dutch newspaper. It said, "This is the monument to the researchers who found our bike route." Nonetheless, newspapers say we have 20 cities, you shouldn't even bother trying to solve that. So what to do? Well, Kel Helsken and I thought, well, let's try to do bigger. We tried to do a problem that was 100,000 times bigger than 20. So we had 2 million stars. We worked very hard, but we're not able to solve it. But we come close, right? So we have a tour. So Kel was mainly involved in finding the tour. Now I was finding the LP bound. But these numbers are very close. You take the ratio, you don't get 1.5, you get 1.5 zeros and a 7. Very, very accurate solutions. But of course, we didn't solve it. There's no application, of course, in these stars. But it did do something that I've always wanted to have. They then wrote up a story about it in a science fiction magazine. I like science fiction. So I really like being compared to the Hitchhiker's Guide to the Galaxy. This past year, together with Dave Applegate from Google and Kel, and Andre Roa, who now works for Meta, we actually went up another factor of 100. We solved problems, didn't solve, but got good approximation for points with 100 million stars or over 200 million. So we have 1.00018, which is good, but actually would like to do better. The reason is that commercial integer programming code like CTEX and Groby, if they get 1.001, so not the 8 there, so 4 zeros, they say you're optimum. They're done. They stop. So if you say they're optimum, it's optimum. So that's what I would like to achieve. We're close, but not there. This was part of a sequence of astronomy problems that we tried to tackle, starting with that one that we solved, 109,000, going up to 1.3 billion. Except for the small one, we didn't solve any. We failed every time. And not only failed, the approximation ratio is getting worse. Here there's 5 zeros, and it goes to 4, 3, 2. It's getting worse. The main reason it's getting worse is the linear programming problems are getting very difficult to solve. So when you're doing a cutting plane method, you have to solve many linear programming problems. You solve the problem, and inequalities resolve. So the simplex method is great, because the simplex method can start from its current solution and re-optimize this very quickly. The trouble is that the simplex method gets difficult, not for these two small examples, but already on 2 million. This was the log. This was the log file. It's taking 99.99% of the time, the simplex method. The simplex method doesn't parallelize. No good parallel implementation. So to move to larger examples, we needed to use other LP technology. For the 2 million one, we just did randomization, right? It doesn't parallelize, so we used 32 cores running the cutting plane method independently with different random seeds. And at the end of the day, we shut down the 28 of them and gave their inequalities to the other 4 and repopulated everybody with the best one. So stupid, but it allowed us to keep going. Once you get up to 10 million, you just can't use the simplex method at all. Unfortunately, there's another LP solver, due to Karmakar, interior point codes. And they parallelize up to, say, 32 cores. The trouble is they don't have that restart capability of the simplex method. You use the interior point code, and you add inequalities, you have to start over again. So to get this bound, I solved only 7 LPs. I didn't just give a few cutting planes, I get many cutting planes. And the problems each solved, 172 hours, that's about a week on a 32-core machine, which is okay. The trouble is, it took 750 gigabytes of memory, and it's just impossible to do a larger problem. There's no machine in the world that would allow you to solve the 100 million node problem that way. All right, so to move to the 100 million node problem, we actually just solved 1 LP. I gathered as much as I could LP inequalities that I think were good. Gave it to Dave Applegate, who works at Google. Dave Applegate is leading a team to develop a linear programming solver that's capable of getting not an exact solution, but approximate solution to very large problems, first order method. So I gave them the solution at Google, and it took them about a year. I think of this, I gave them the big LP for these 2 problems. It took about a year for Google to finally adjust their codes in order to handle instances large, but this past April, so April of last year, he sent me, they did sort of Primal solution, but sent me the dual solution, which is what I wanted. I couldn't believe that he got it. I mean, this was a huge problem, 50 billion non-zeros in the matrix. It's unbelievable that they worked on 1,000 processors, each independently doing their steps of their first order method. That's amazing that they did. I still don't understand. I understand the math, but how they carried out the computation, I don't really know. And for Google, of course, they want to go bigger. I want to just solve this one. They want to go bigger. So we made this 1.3 billion, and I also shipped that off to Google, an LP, because I think if we can actually solve the LP, we'll at least get a third zero there. The bound we currently have is just a simple thing, getting a dual solution independently by each region dividing up. So that's what Google wants. Google is just using these TSP in order to drive their LP technologies. They wanted, which I don't know what they want to do, but they somehow want to solve big LPs within Google. I don't know. Whenever I ask Dave, goes, I can't tell you that. So I want to solve this LP. We don't quite have it, right? We have this 3 zeros and a 1. I'd like to get rid of that 1. So we currently have a gap between the Tor and the bound. And the gap comes from 5 different sources. First, Kel Helskin and Andre Roa were responsible for finding the Tor. Well, I think their Tor is good, but there's some gap between what they found and what the optimal is. So that's contributing to the gap. Or now, I'm collecting all cutting planes, but and no one knows the full list of cutting planes. So there's some gap between the optimal value of my LP and the Tor length. All right, but Dave's code is not actually solving the LP, it's just getting a good approximation. So there's some gap between the LP value and what they produce. Then there's a further gap by somebody in a column generation for the TSP. You actually have 100 million squared variables. I couldn't give Dave all the variables. Besides choosing inequalities, I had to choose a subset of variables. And then he gives me the dual solution. I had to adjust it to get it bound. That means that we paid a price for not having all those variables down. I had to adjust his dual solution to take into account of those variables. So that one I actually know. That was 3% of the gap was because I didn't give Dave the right columns. Now, in computing this price bound, what I did for every edge, it gives you an estimate of of how much the LP really wants to use that edge. And this was useful. I sent that information to Kel, and over now the past 10 months, he's been, each day I check his server, and he always finds a little improvement in the tour. Altogether, he improved the tour by 8.6%. Hopefully that keeps going. Right, so now we're down to, instead of that 7 up there, now we're down to a 6, getting close to making that a 5. Where's the rest of the gap? I believe that is my fault. But Dave is probably getting a nearly optimal solution. I probably just don't have the right inequalities. So right now, over the past 2 months, at a cluster of machines at Waterloo, I've been finding the next LP, getting more and more cutting things. Plan to ship them to Google in April, then hopefully this summer. Hopefully we get another year. So that's the big problem. What's the state of the art? I mean, we can't solve those, but there's smaller instances we can't solve. The most famous one, or most recognized one, is due to Bob Bosch. He has this book called OptArt. He uses optimization to make little art drawings. He can draw the Mona Lisa with just one line, never changing the line. Not the kid on 100,000 points. This is on the cover of books. It's been in art books. There's even on a television show where the tour is present. Certainly the most recognized example is the TSP. Yeah, we can't solve it. All right, the approximation has 4 zeros. A little bit more work is fine, but we can't solve it. What I'm drawing here, you might see it's a little bit of a color. If I zoom in, it looks like that. The black edges have value 1, the red edges have value half, and there's colors in between. So what needs to be done is to look at that vector and find more inequalities, more cutting planes. This is the heart of the TSP now, getting found. You get a large vector like that, how do you find valid inequalities? And I think it's a nice area in that it combines the optimization, graph theory, combinatorics, algorithms, computation, engineering, all stirred together to drive the process further. One nice thing that happened with this, and this took a lot of computation over the years, that I've been working on proving certain edges cannot be in an optimal tour. And what remains now is a planar graph. So I've reduced this problem from the complete graph down to a planar graph. So I've colored the faces to show it's planar. You zoom in. So I know four colors suffice, but 38 colors also suffice. So it's a planar graph. What's nice about a planar graph is they have a dual. You get a dual graph by putting a point in every face and the edge crossing the prime edges. Nice thing about a dual is a spanning tree in a primal graph. You take the edges not in the spanning tree, they give you a spanning tree in the dual. So they come in pairs. That's important for the TSP. You know, the TSP connects it. It's not in a spanning tree, but it connects it. That, simultaneously trying to build a spanning tree in a primal and a dual, allows you to prove just a remarkable theorem of Igor Rivin. So the trouble with subtle inequalities, there's exponentially many of them. What Rivin shows is that for a planar graph, you can go up into a higher space. Rather than having the number of edge variables, you have 3 times the number of edge variables. But the number of constraints that are just linear. So you have a small LP whose projection gives you this big subtour LP. So that's always been my dream. I mean, I learned about this result from Michelle Goldman 15 years ago. And I've been working, trying to get one of these big LPs to finally be planar. Because now I can live, I dream of living up in a Rivin space, completely solving the LP up there. So this happened 2 years ago. The only thing I've done so far is that, well, now you can solve it as an integer program problem. So I bet this running time was 32 cores for half a year, but it increased the bound by 6%. It's not going to solve the problem, but it makes me think that algebraic methods maybe can do some more. So 100,000 seems like something we can't do. So we need help solving 100,000. This was a problem made by David Johnson, just not a nasty problem, just random points. We can't solve it. I can't make this planar, but I did reduce it down to a graph that has degree 5, so a sparse graph. Maybe more importantly, 26,000 of the edges have been able to prove they are in the optimal tour. So you have some information. But again, we can't solve it. Well, 100,000 is big, but even smaller there's some difficulties. So this is a histogram of the running times for 10,000 instances with 1,000 nodes. That's all nice, except for these are the logs of the running time. Right? You're getting a nice Gaussian distribution, but they're the logs of the running time. That means you have a big variance between the smallest and the biggest. And this was noticed actually by David Johnson. We're working on computing, estimating some TSP constant. I just wanted to solve a problem, so I'm really happy to solve 10,000 problems. I sent it to David Johnson. David Johnson unfortunately died several years ago. This one of the last lecture he gave. Yes, it's showing the histogram. Yeah, this is so problematic for me that Concord produces this. It's somehow like if something goes bad in the code, they multiply. That's why you're getting this log runtime. So I checked a million examples on random instances on a torus, and again, it has this bell curve, log times. To see why this is a problem over the past few months, I tried to solve 1,000 instances with 10,000 points. Well, 800 of them solved in 10 million seconds. Each processor, each core running 10 million seconds. And again, you see it's getting the start of another Gaussian distribution. So if you project out, it says the difference between the easy problems, which were about 7 hours, the hard problems would be 7 years. Right, so Concord definitely cannot, we cannot say that, well, yeah, we can handle any 10,000 node problem. It certainly needs help. And I hope some of you might consider helping. The question is, why should you? TSP is studied, I was just trying to convince you to start working on the TSP, but why should you? Well, for the community, many of the household names in discrete optimization come from the TSP. So using LP just to get bounds, that's from the TSP, or cutting planes, branch unbound, simulated annealing. These all came from TSP research. So as a community, if you can help us develop new techniques, this engine of discovery, community would be grateful. But why should you personally work on the TSP? Well, we like winning contests. Kel Helskin and I, several years ago, won $17,000 at the end of your Kaggle competition. I don't know any of you involved in Kaggles, but there's these leaderboards and trash talking saying these old guys are not going to sell themselves. But in the end, our team won all the first prize on all three contests. But I have to say, it's not all a happy ending. This team from Japan, the KM Coders, this past January I competed again and they won all the money. Top. My team, I worked with students from Moscow. We came 6th place. We didn't get any money. All right, so that's not, you don't always win. But if you want to appear in Korea's one and only mathematics, TTSP man. I competed a tour for Pokemon Go. And not only that, the following year, the magazine gave me a fake award for the pubs thing. That people like beer and mathematicians. Not only that, you might notice a difference between that photograph's hair and my hair. They gave me extra hair to compete with Peter Schultz. That's a big award. But if you're more interested in real awards, the TSP can also help. So this is Ola Swenson won a $100,000 Held Prize. Actually, it's the same Held from Held Card. It's that Held. Held Prize in 2019 for his TSP approximation. But Vera Traub, last year she won the $50,000 Mayor's Economy Prize for TSP work. Now you might know that prize. That's the same one that the famous mathematician Professor Park won, Jun-Young Park won. So this is the award ceremony. It's on national television in the U.S. The ceremony is being announced by two well-known actors in the U.S., including Danny DeVito. So what I'll show is a film. It'll transition from Jun-Young Park's award to Vera Traub's award.
Vera Traub works in combinational optimization. For example, traveling salesman problems. Questions like, if you have to make a delivery in several neighborhoods, what is the most efficient route that visits each of them only once? I'm glad you got all the big words. Yeah.
So that's them, actually, this is on stage, Professor Park, Professor Trout. This is a person you may not recognize. That's a famous rapper, and he was in the Black Eyed Peas, named Will.i.am, big promoter of science. So if you wanted me to rap star, maybe we should work on this. If you want to meet your president or prime minister, that also might come through the TSP group. These are 5 of the mathematicians I mentioned in a talk, each meeting their head of state. One meet the president, that may be the way to go. But I think the most quickest way of saying why you should work on the TSP, this is Richard Feynman. He was Nicholas Christopher, he was at Stanford and met Feynman and explained to him that he's working on the TSP, explained what it was. Feynman just coincidentally met him in a lounge. Next day Feynman comes back, yeah, that sounds like a hard problem, have fun, kid. Right? So that's a TSP, it's this great challenge. Somehow it's in a simply stated problem, capturing all the complexity. And you can certainly make progress in general optimization by working on the TSP and maybe have fun. So Richard Karp, great computer scientist, said the most thrill he ever had in his work was the night the computer numbers are coming up on his work with Michael Pell. Harold Kuhn, you might know the name from Kuhn Tucker, Zach Kuhn, Karush Kuhn Tucker. He said he worked on the traveling salesman problem for 48 years. Right, so it must be something there. Christoph Pastamich said the traveling problem is not a problem, it's an addiction. and it's not one I'd like to overcome. I mean, just the opposite. I know candies with rappers at TSP challenges, so I have to get people on it. Because again, the TSP, I believe in optimization, there's breakthroughs on the horizon, not just for the TSP, just need new ideas. So maybe you can help contribute. Thank you.
Thanks for the nice talk. It's time for other questions. Any questions?
Don't you have to consider about TSP problems that doesn't satisfy the triangle inequality? Does that work differently?
Well, certainly, so the main class of problems that don't satisfy the triangle, you're given a sparse graph, and you want to know, does it have a cycle? That claims all knows, Hamilton cycle. Because there you can't cheat and say, I take the shortest path, because it won't be. And so those ones, our code doesn't work very well on. It works very well on getting the bound, but our heuristic, like Held-Helston's algorithm, doesn't work very well. You don't satisfy the triangle inequality. So it's the only warning that comes with the Concord code. It says, don't use this for Hamilton cycles, and then people write papers like Concord doesn't do well with Hamilton cycles. So,
Any other questions?
Can I ask one question?
Sure.
So it looks like you are using your problems to get a bound, but these kind of, if you do some computations, this computation might have a floating point errors or numerical errors.
yeah.
Do they actually play any roles?
Yeah, of course they play, well, as I mentioned to it. One is when I say solve this problem, we actually solved it. Because I mentioned that the new programming rule is such that even though the commercial software gives me a solution at floating point and doesn't satisfy the inequality, I can adjust it. So our lower bound is computed in fixed point arithmetic. So I take a floating point number, make a fixed point, 32 fits on decimal point, 30 fits on fraction point. So our bounds are actually accurate. So when I say we solve a problem, solve it. The thing is though, we're not doing Euclidean distance. It's Euclidean distance rounded to the nearest integer. So you can increase your scale, but you're not getting the irrational distances. And I've been trying to do that, but I could solve like about 500 points. I wanted to solve 1,000. But the trouble with irrational distances, it's very difficult to say whether one two are shorter than the other. You're doing sums of square roots. No one knows how in polynomial time saying that this sum of square roots is less than that sum of square roots. You tell that they're not equal using this field theory, but you can't know that. So, so far I haven't been able. Nonetheless, I'm trying to get around that, and I could do about 500 points. So in that case, we're not doing those. Oh, that's very good. Just running around.
The question here.
you said that for the optimal solution of TSP problem in the planes, you cannot have crossing. So how about, is there some insight for the 3D case? Is there some similar reduction for the...
In the 3D case?
Yeah.
Yeah, I don't know. I mean, I didn't mention, but one of our main ways of finding cutting planes is that the fact the LP solutions, because they don't tend to cross, the LP solutions tend to be planar. We take advantage of planarity. In 3D, the solutions are wildly non-planar. Like you can kind of hook together, and so I don't know a similar thing in 3D.
Are the modern day TSP research concentrated on trying to lower I find the LP bounds, all concentrated in the LP, trying to solve the LP?
Well, I think for TSP research, it's more to get the LP bounds to find better cutting planes. But I should say that if you count the number of papers, there's far more papers on finding tours than there are getting the bounds. So I was saying in our meeting, we have two cats, Andy and Keith, two black cats. And because there's all these papers about animals solving the TSP, so I took the two black cats, one of them is smart and one of them likes snakes. So I made 7 bowls and 1 piece of food in each of them. And they're both outside, and I only let the one that likes to eat in. The smart cat's looking through the window. So the one that likes to eat realized the smart cat would get the food, so it goes around and gets all the 7 bowls. And I filmed it, and I get a pretty good tour. And I said, look, a cat solution to the TSP. I put it on Twitter. But then somebody wrote, no, this is already a thing, and pointed to a paper called Cat Swarm Algorithm. TSP had over 300 citations. So there's many papers in that aspect. But they're not really trying to solve problems exactly. Exactly, I would say the most important thing is finding cutting planes better. There's not much research on it, but that's where the big help would come. Yes?
Depending on the cutting plane problem, like depending on which point to start to solve the intersection, we can solve it different ways. So those combinations have a big part on this solving this problem or no?
Having in different ways?
Yeah, like when you have 4 points crossing the intersections, and like depending from which point you choose to solve this problem, you can have different results.
Yeah, well, there's certainly many different optimal solutions.
Yeah.
I mean, so
those randomization has a big impact on that, or like, is there any way to choose from which point to start solving this intersection problem?
So for the term thing, when we get a circle, it doesn't matter which way you come back. But for heuristic methods, so if you just say to do the nearest neighbor algorithm, you always just go to the closest point. It depends on which one you start. So probably you should sample.
I have my own question.
Thanks.
So when you pass the large LP problem to Google, so how big was the file?
Yeah, that's a good question. It was very big, and so I actually wanted to put it on a disk drive and just take a bus to go.
Wow.
And they didn't want it, so then what am I going to do it on a disk drive? Because their servers are not in Google Research New York. So for the smaller ones, he had set up just a way of Google transferred things into it. So from Waterloo, I had a connection, it took about a day to transfer.
A day to transfer?
Well, several terabytes.
Wow.
So it's coming from your machine. For a large one, it's even bigger than that. It was like maybe 4.
I was thinking of like some gigabytes or something, terabyte.
No, it's in terabytes. And Google didn't allow, for security reasons, couldn't keep that open. So it took them a while to figure out a way to work it. Yeah, it's definitely an issue. Yeah, there's definitely more gigabytes. That's 5 billion non-zero.
Billion already.
Yes.
You showed that on randomly generated instances, the computation time can vary a lot in the log Gaussian. Are you able, when you give real-life instances to the solver, to have an idea or a bound for the computation time?
Yeah, I think that's where maybe, I don't think machine learning, deep learning is a good tool for getting towards, but I think deep learning might be a good idea to say, this one's going to be hard, you should work harder. So I still solve those big problems. It's not that I waited thousands of years. I just realized, oh, it's hard, and I turned on more problems. So I think one thing, if I can post that running time for those 1,000 instances, maybe somebody could do some sort of deep learning to figure out what's different. Because if you draw 10,000 points randomly, they look the same, right? I mean, but there's something happens in the computation that makes them different. It'd be nice if machine learning could detect that.
On the same topic, there's they started with simulated annealing, and now there's new methods that propose like physically inspired algorithms to try and find satisfying solutions to such NP problems. There's a lot of claims being made with new ones like simulated bifurcation. And one good thing about it is that the running time is fully controlled. You take instances, you make it run for some time, there's a number of iterations, and then you can have a solution which is it's at some good. And from an engineering perspective, like in semiconductor manufacturing, you have a solution that's okay, and you do it and go on. How do you think this could, like, as someone who builds and sells a solver for the TSP and some of the same sort of problems, how do you think it concurrences solvers, those methods that are more general, that have like short compilation time, which seems to be one current problem of the complex solver?
Yeah, so yeah, it's true that we find a good toward, and the hard part is getting the bound. So you can stop when you want. I mean, these approximations probably, in reality, if you're driving, you don't have that accurate of distances. So probably we can stop early. So I think, as I was discussing, for genetics it's different. For genetics, they're really saying the gene looks like that. They really want the optimal solution. But even there, they were running heuristics many times, and the heuristic was probably producing an optimal solution. But they had to run a heuristic so long, it was shorter to find the optimal solution rather than run a heuristic. So they had no way of knowing when they should stop. They kept running their heuristic until the heuristic didn't ever produce any more things. So I think in practical situations, you more want to do heuristic methods rather than exact methods. The nice thing about these exact methods, I said, they have a trickle-down effect. So you're producing techniques that are used in other optimization. That's the main practical reason for continuing to work on optimization techniques.
Because on the instances that are on the right edge of the computation times that are very long, is how much of the time spent computing is during the last 10% or during the last percent to
well,
reach
it's
the optimal
the last thousandth of a percent. It's a so and on almost all those long instances, Helskin already told me that the solution was optimal, which is all this time is proving it.
Okay.
Yeah.
Thank you. So I think it's time to wrap it up.
Yeah, thank you everybody for coming.
Thank you very much.